Welcome. Welcome everybody back to the online SPICE SPIN+X seminar series. I'm Jairo Sinova, and I organized this series together with Libor Schmekiel, Angela Wittmann, and Kajana Versosute from SPICE in collaboration with the SPIN+X Collaborating Research Center led by Martin Asliman, Burger Hillebrand in Kaiserslautern, and Matthias Globe in Mainz. As you know, we're going to begin to have once again more of these talks interspersed between the conferences that we are now having today. After a few weeks of hiatus, I have the pleasure of having Jose Baldovi, which is the director of the 2D Materials Lab, Institute of Molecular Science, ICMOL in the University of Valencia. He got his PhD in Nanoscience and Nanotechnology at the University of Valencia, and with a Mercury study at the MPI of the Structural Dynamics and Matter from 2017 to 2019. He came back to Valencia and is distinguished researcher in 2020, and since 2024 is a distinguished researcher as excellence at ICMOL. He's an expert on two-dimensional systems, chemical design, or smart molecular interface with two-dimensional devices, dimension of underworld materials and heterostructure, and has a lot of interdisciplinary aspect between chemistry and material science and transport and magnonics, spintronics, and particularly looking at sensing of devices. He got recently the ESC Starling Grant and several prizes such as the Science and Technology Prize, Situat dal Gemessi, and not Matmol Respicit Thesis Award. So with that, I'd like to thank Jose once again for joining us, and I will give you the floor to go ahead and please start your talk. Thank you very much.
Thank you, Jairo, for the invitation. And I accept apologize because I understand that sometimes they have trouble with the computers. So I'm gonna talk a little bit about the research we are doing here in the University of Valencia. I'm the director of the 2D Smart Materials Lab, and we are doing theory and simulation on van der Waals materials using always first principles. So as you know, most of the applications that we are using in daily life are based on electronics, are electronic applications that process information by means of electric current flowing through a conductive material. As electrons move, they experience a scattering that leads to electrical resistance, heating, and energy dissipation. And this is an important bottleneck for the future miniaturization of the devices, because this Joule heating, it will affect the performance of these devices when we are going to smaller dimensions. But as we all know in this audience, the electrons have another fundamental property, that is the spin, that can be used to store, process, and transfer information in the form of spin waves. So just let me this here. So similar to the flow of a Mexican wave in a stadium, the electrons are not moving, but the information is transferred through the material via magnetic collective excitations. And this can provide ultra-low cost nanodevices with wave logics being also relevant for quantum technologies. And very importantly, this is now a very hot topic. It's happening right now. So here is the first magnonic roadmap that was published in 2021. Where the leading experts in the field identify the main challenges that are excitation of low wavelength magnons, how to manipulate them in the nanoscale, the creation of nano devices with low Gilbert damping, and also the interconnection with standard electronics. More recently has been published, well, now is accepted, the 2024 magnonic roadmap that is also pointing to the miniaturization of these magnonic devices. So I'm sure that 2D van der Waals magnetic material will play a relevant role in the future, because they are at the limit of miniaturization. They have a lot of possibilities for tuning the properties, for example, using van der Waals stacking, and are integrable with silicon technology. And this is the main focus in our lab. So this is just to recap a little bit the history of 2D materials. So everything started in 2004 with the isolation of a monolayer of carbon atoms, the graphene, and all the research during these years, the opening of this new field to the Nobel Prize to Gaim and Novoselov in 2010. Then after 2010, started the people to do research with semiconducting 2D materials, for example, molybdenum disulfide, the first molybdenum disulfide transistor. And in 2013, it was the dream of Richard Feynman to combine different properties in one material using different layers. So this has been very active, but magnetism was not in the main attention, because people were trying to induce magnetism in graphene, but there was not any single 2D magnetic material isolated. So it happens in 2016 with the isolation of this family that they are intrinsic to the antiferromagnetic material, the transition metal phosphorus trichalcogenides. Then 1 year later, the first 2D ferromagnet that is antiferromagnet when you have several layers. So it's very useful also for spintronic applications. And a very hot topic now to stronics that appeared in 2018. Even people now are combining both fields. So here are the materials we are studying. We started doing some calculations and we have been continuing this research with transition metal phosphorus trichalcogenides. They have Néel temperatures are between 70 and 150 K and are quite stable. In the case of chromium iodine 3, this is the first 2D antiferromagnet and is antiferromagnet between the layers. As I said before, it has a Curie temperature of 45 Kelvin, and it has been deeply studied. It has a ferromagnetic honeycomb. And more recently, it has been developed the chromium sulfur bromide that appeared in 2021 with a higher Curie temperature of 150 K and air stable. So it's very, very interesting for to do research with this material. So here is the computational and theoretical framework that we are using in our group. So we start using first principles, density functional theory, using Hubbard corrections, because we have a strong correlation in the d orbitals. We're dealing with magnetic materials. Then we go through a process of vannierization. So we use the Vannier 90 code to obtain maximally localized Vannier functions, using, for example, in this case, the d orbital representation. And we connect with the TB2J, so from tie binding to exchange interactions to have all the magnetic interactions, the spin Hamiltonian. So we calculate magnetic properties. Then we have we can calculate magnon dispersion, and also if we apply Landau-Lipschitz-Gilbert theory, we can simulate the real-time, real space propagation of the spin wave, so the spin dynamics. I will start with the studies in chromium sulfur bromide. So to start, I will start with the chemical structure. The material crystallizes in a orthorhombic structure. And as we can see here, these chromium atoms that are the magnetic atoms, they have different bonds depending on the direction of the space. So along the A direction of the crystal, we have sulfur and bromide. They are forming almost 90 degrees bonds here. Whereas if we go along the B direction, that is the easy axis of magnetization pointing to, and we have these sulfur bridges of around 160 degrees. So this is an isotropy in the structure. This is just a crystal field representation. We are taking now the one chromium, and it has this distorted octahedral. This is the B axis in the material. This one is here in Z. And with this, we can have the crystal field splitting. So we have 3 electrons that are doing a spin of 3/2, and we have empty here, e.g. orbitals. This is reproducing the electronic structure. Of course, we can see 2 things here. The one is the anisotropy of the crystal that makes that from gamma to X, that is parallel in real space to the A axis. We have no dispersion here in the conduction band, whereas from gamma Y, this is very dispersive. So the material behaves kind of 1D electronic system. And if we take into account the projected density of states, we can observe here this spin up T2G orbitals that are filled. we have the EG spin up empty, and of course, all the down components are empty. With this, we can take now our projectors to the linearization. So for the tie binding model, we're going to select the d orbitals of the chromium, p orbitals of sulfur, and p orbitals of bromide. And we have to calculate the minimal spread of linear functions fitting this electronic structure. We can reproduce the electronic band structure with these projectors. Then regarding the magnetism, these are the first neighbor, second neighbor, and third neighbor interactions that are the most important in this material. We can observe that first neighbor are these two atoms that are contained in this line along the A-axis. So this is J1. J2 is between the chromiums that are from different planes, these two, and J3 is along the B direction. So in this case, we compute using 3 Vannier Hamiltonians. We add the spin orbit coupling, and we point the spins are pointing along X, Y, and Z directions. And with green function method in the TB2J code, as you can obtain it here, we compute the magnetic exchange interactions for different Hubbard-U. One interesting thing in this material is that when we were studying the magnetism, it appeared this work that published afterwards by Lopez Paz in Nature Communication. In that time was an archive, and they were measuring how is the evolution of the crystal structure with temperature. And we can observe here that the A-axis is expanding when we go to low temperature, whereas the B and C axis are being compressed. We calculated, taking into account these lattice parameters, following the lattice parameters trend, and relaxing only the atomic coordinates, and we were computing all this exchange interaction, and we can observe that for all this range, the J1, J2, and especially J3 are increasing. So the magnetism is driving this structure until it saturates at around below 40 Kelvin. The structure is not moving anymore. This was published in this work in Advanced Material in 2022. And then once we have this idea that the lattice parameters are changing with the magnetism, why now we cannot take advantage of the outstanding deformation capacity of 2D materials, and now using strain engineering, so straintronics, to control the spin wave propagation. This is the main topic of this work that was published in Nanoletters. This is the beautiful artwork that the Quasar Dynamics made for us for this cover. And we started computing, so the effect of a strain on each one of the exchange interactions. So we are calculating J1 for different strain levels and varying also the Hubbard-U. We can fit to this to the least squares method, no? And then we can calculate these high density maps of magnetic exchange. This is applying uniaxial strain along the axis, A axis. And this is along the B-axis, and we can observe how is the evolution of J1, J2, and J3. Interestingly, as I said before, J1 is very connected with this with the A-axis. So we are here making this strain along the A-axis. We're expanding the material, and J1 is clearly increasing, is following this. And we wanted to understand what is the main effect doing that, and we go to a orbital decomposition of each one of the exchange interactions. This is something that TB2J allows, and we find these two different pathways that are competing. This is a T2G from EG orbitals, that this is a ferromagnetic pathway that is here, is not being very affected by the strain, but we have here a T2G to T2G interaction. This is the DXY to DXY orbitals that in this case is antiferromagnetic. And with this expansion, we are fighting against this mechanism. We are making it less antiferromagnetic, and then the J1 is increasing in the material. Then we go to the J3 that is connected with there are two atoms that are along the B, connected along the B axis, and in this case we have the opposite. This is a negative sign. This means a compression makes an expansion of J3, is increasing, and there are these two mechanisms, the main responsible of these interactions. In this case, this is the ferromagnetic mechanism from T2G to EG orbital, mediated by this sulfur atom. And in the case of the antiferromagnetic is EG-EG. And this competition with this compression, we are minimizing the antiferromagnetic pathway here. This is the diminishing, and we are increasing the ferromagnetic character here, the overlap here. So that's why we can increase J3 with this compression. This also affects, of course, the Magnon dispersion. Here we are calculating via Holstein-Primakov transformation how the Magnon dispersion evolves with an expansion of the material. So this expansion of the A-axis, in this case, by uniaxial strain, we are having this increase in the dispersion. So this is the final plot here, and especially we are affecting the magnons in the gamma X direction. So it's a selective control of magnons in the material. With this 5% increase, we can observe here this blue line. And the opposite is happening for the uniaxial strain along B. In this case, we are now increasing the lattice parameter, we are decreasing J3, and we are affecting especially the gamma Y direction in the opposite way. Now, this compression makes more dispersion, so it will make the spin waves to travel faster. Then we could like take from using Magnon dispersion, the Magnon dispersion relation, but then applying a spin wave theory, we can calculate the magnetization. We predicted 122K, the experimental is around 150, so it's quite close. And we observed this enhancement of the Curie temperature. And then we are applying the strain to evaluate two things here, the Magnon gap and the Curie temperature. In the case of the Magnon gap, we can observe here that it's increasing when we are applying a strain along the A-axis and also increasing the Hubbard-U, but this is not translated here to increase in the Curie temperature, because in this part of the spectra, the interactions, we are favoring the antiferromagnetic mechanism. So the best strategy for increasing the Curie temperature in this material is just expanding along the A-axis. Whereas in B, we have the opposite behavior. So this is clear. And this white part here is because we could stabilize antiferromagnetic ground state in chromium sulfur-bromide with extreme Hubbard-U calculation. Then regarding the spin dynamic simulation, so we apply Landau-Lipschitz-Gilbert equation. In this case, we are applying Gilbert damping from the literature, like we are taking from chromium iodide 3. This is just empirical for chromium iodide 3. And we apply an ultra short oscillating magnetic field during 1 picosecond to generate a spin wave. Here we can observe the effect. This is with the material without any kind of strain. And here we have compressive strain along B. And we can observe how the wave is traveling faster along this Y direction. This is following the B-axis of the material. So according to these calculations, we can achieve group velocities of 7.5 kilometers per second with this apply 5% strain on the B. So it's a way of controlling the spin waves velocity. Then another way of playing with magnons in this material is to propose now the chemical control, the molecular control of magnonics into the van der Waals material. And the idea is to use the power and versatility of chemistry to excite, modulate, and detect the spin waves in hybrid materials that will have a molecular part and a 2D magnetic material. Here is a 3D animation of the idea. Here is a coronine molecule that is sublimable. It has been proved in several surfaces like graphene or molybdenum disulfide. And now we have a magnetic dipole between the molecule and the 2D material that can be, for example, producing excitation in the energy levels of the molecule. We can affect the spins in the surface and create a spin wave. And then one can think to use another molecule to detect this propagation of the spins, a way of making molecular control magnonics. We have started with organic molecules. We have started with coronine, perlin, and TTF. All of them are donors. And we also wanted to test an acceptor molecule, very popular, that is in this case the TCNQ. All these molecules were selected because they are flat, they have proof hybridization in several substrates, and there are the first steps to start with this study. To do this kind of calculation, so we need to test different absorption sites, also the orientation of the molecules using rotation along the phi axis. We have to build supercells because we want to study the effect of individual molecules in terms of hybridization and effects. Of course, then we can also model a kind of monolayer of molecules, and we add always dispersion corrections. We calculate with this formula the absorption energy, that is the total energy, the ground state of the hybrid, and we subtract the ground state of the 2D fully relaxed and the 2D material and the molecule. This after the full optimization, we were also testing the orientation, as I said before, and here we can observe this as the absorption energies according to this evolution. Now, in this case, the perilene, coralline, and TCNQ are in this position that we have here, but in the case of the TTF, we need to rotate, like it was around 165 degrees. This is the minimum energy, because the TTF, the sulfur atom is like pointing towards a bromide. We have here the absorption energy, so it's clear that the TTF, and once we know that, we also add a methyl group to make it more donor and to have more absorption energy. And this is the distance between the molecule and the surface. In this case, it gets closer and it provides more charge transfer. So we are increasing the donor character of this molecule. We can control the charge transfer that is donated to the substrate. Here are the charge density representations. In this case, this blue cloud here means a depletion. So it's a donor, it's donating electronic density, and the bromide is accepted. In this case, TTF-CS3 and TTF, they are the molecule is bended towards the substrate that I said before. And then it's coralline and perilene, they are also donating, and the acceptor, the TCNQ, is not providing any kind of charge transfer. When we plot here the charge transfer, that this is the calculated charge transfer for these molecules, there are these blue dots, and we compare with the energy of the HOMO of each one of the molecules in gas phase with the conduction band of the chromium sulfur bromide. And we observe this linear relation that relates depending on the energy of the HOMO and the acceptor, we can predict the charge transfer that each molecule is going to donate. This is a perfect agreement, the calculation with the full system and this prediction with this subtraction. Regarding the effects of the molecules, we can observe one thing, that this is the chromium sulfur bromide, this is along the y-axis. This is the angle in the fully relaxed chromium sulfur bromide structure. The molecules are increasing this angle. This is detrimental for J3, because when we are increasing this, we are making more, we're favoring the antiferromagnetic pathways, and especially when more donor is affecting more. And this has an effect here. If we take just the distortion, we remove the molecule from the calculation, but we have the distortion that each molecule is doing on the chromium sulfur bromide. We observe here in J3 this decreasing. But when we add in the calculation, when we have the molecule, we activate then this charge transfer. And here is important that this is increasing clearly, and especially for the molecules that are more donor, the TTH, TS3, and the TTF. These are increasing the J3. In all cases are increasing from the distortion, but in these cases, even from the pristine material. And as we can see, the TCNQ, that is not doing any effect, it keeps just the distortion. It's the only thing it's doing on the surface of chromium sulfur bromide. This we can now test if we just take a unit cell of chromium sulfur bromide and we add a gating, like we are simulating now this charge transfer just in the unit cell, we can obtain pretty reasonable exchange interactions. This is the J1, J2, and J3. That the red is J1, then we have here J2 and J3, and we can observe that they are pretty close. So the main effect to tune this exchange interaction, the magnetism, is due to the charge transfer. So now we have simple rules to do high throughput screening of different molecules and see what is the effect in the magnetism. This was the effect of distortion, but important here is to compare the doping with the molecules in just one unit cell. All this has an effect in the magnon dispersion, is affecting the optical magnons, especially here. We can see the TTF and the TTH-CS3 here. This is the main effect comparing to the pristine that is in black. And we are affecting especially in this gamma Y direction. So this bond of sulfur is the main thing that we are affecting, and where the charge transfer is, we are modifying these two competing mechanisms that I showed before in the magnon extra intronics work. Then we have been also studying chromium iodine 3. In this case, it's interesting because it has some ferromagnetic honeycomb, and this provides in the magnon dispersion direct dispersions that can also have a gap opening that leads to topological magnons in these systems. This has been experimentally measured. In the case of chromium chloride 3, this is a direct cone, is not any gap. This material has less spin orbit coupling, and the TC is around 13 Kelvin. That's also important in this case that the spins are in plane, is something characteristic of this material. In the case of chromium bromide 3, there's discussion in the literature, but it doesn't look that there's an opening of the magnon gap. But in chromium iodine 3, in these measurements at 4 Kelvin by inelastic neutron scattering, we can observe clearly this opening here in the K point and the K points of the magnon dispersion. So we wanted to simulate this using a fully first principles approach. So in this case, there are 0 parameters in our model. And then we also want to add biaxial strain. So for each case, we're doing a self-consistent field calculation of the how-are-you following the linear response method that is implemented in density functional perturbation theory in quantum espresso. And we wanted to see the effect also in each one of the strange interactions. So for example, here, when we are applying a strain, we are computing self-consistently the evolution of the how-are-you for each one of the points. With this, we could observe, like when we have here the spin Hamiltonian, so here is the single ion anisotropy, we have the isotropic and exchange interactions, and the Dzialoszewski-Morilla, that in this case is cancelled. We cancel it in the calculation, and we observe the formation of the Dirac cones for the chromium chloride 3, chromium bromide 3, and chromium chloride 3. But then when we activate the Dzialoszewski-Morilla interaction, is this 0% here in chromium iodide 3, these black lines, we can observe the opening of a gap. In the case of chromium bromide 3, it's a little bit in the calculation, but especially here is clear. And with a strain, we can directly control this opening of the gap. So we are here reporting the evolution of this magnon gap because we are playing directly with the Dzialoszewski-Morilla interaction. So it makes an enhancement of the magnon gap by 40%. That this is also a new way of like practicing a strain to control directly a magnon gap in a 2D magnetic material. Then we have also been working with transition metal phosphorus trichalcogenides. As I said before, this was in 2016, the first isolated 2D antiferromagnetic material. The interesting thing about this family, well, it has a honeycomb lattice, but also depending on the transition metal, we can have different magnetic orders, different distribution of the spins. In this case, for example, for iron, we have these zigzag chains that are antiferromagnetic. In the case of nickel, are zigzag chains, but in this case, the spins are in plane. Here is out of plane. And for example, for manganese, we have nail distribution. So, and all these works point towards the measurement and prediction of magnons in this material. In collaboration with the group of Mirko Cinchetti, that I think is the next speaker in these seminars. So we were simulating the ARPES measurements. So they were measuring the valence band electronic structure in iron PS3 that are the experimental results. And we were using this Vanier approach. In this case, this is plot with Vanier tools coming from Vanier orbitals. We could reproduce the measurements. So in this case, we fitted this gap here that is around 0.9, if I don't remember bad, electron volts, and we needed a how-are-you of 1.9. That corresponds to the one that is reported in the literature, that usually is like 2.1, 2.2. So with this, we could match this gap here, and then we have these similar shapes here, for example. So we were also revealing the rich band structures and which are the orbitals. So closer to the valence band is dominated by 3D orbitals. Then other calculations we did for these materials, in this case for cobalt, iron, and nickel PS3. This is in collaboration with the group of Van der Zandt in Delft University. And in this case, we predicted with the DFT calculation. So here we are fully optimizing the structure of cobalt, iron, and nickel. And we can observe a compression, a 2.5 compression of the A-axis, and a little expansion of the B-axis is also happening for the iron, but for the nickel is nothing happening. There's no expansion or compression. And experimentally, they were designing these kind of membranes with the material and exploring how the system behaves when cooling down the system, activating the magnetic long-range order. So in the case of cobalt, is observed this compression of the A-axis here and expansion of the B-axis. This work was published last year in Nature Communications. This is here. And you can observe that in the case of nickel, the evolution is isotropic. So here is more clear that isotropic distribution, so it's not any effect. And we were doing this orbital resolve approach to see what is happening with the ferromagnetic interaction. That is the main interaction here along these two atoms, along these two irons, for example, in this case is iron, and along these two irons. So the material had this zigzag distribution. So in principle, this is antiferromagnetic and this is ferromagnetic. If we take into account this ferromagnetic interaction with the compression of the axis, we are favoring this mechanism, the hopping of this electron from this orbital to this orbital. And in the case of the other pathway that is parallel to this B-axis here, we have the expansion of this axis because it's avoiding this, making this more antiferromagnetic, and is canceling this process. In the case of nickel, all these orbitals are filled. So these two mechanisms are prohibited. It's not possible to jump because everything is occupied, and we don't have this mechanism to explain the effect. There's not any effect in the case of nickel. Other idea with this material that we proposed was to study what happens if we have a Janus structure. So similar to molybdenum disulfide, for example, we substitute in this case sulfur by selenium, and we wanted to see the effects of this mirror broken symmetry in the material. This was published in Dalton Transaction, and this is the cover with the Roman god Janus that is looking to the future and the past, because this material has now two phases. Well, we have calculated for the different magnetic configurations. In all these cases, the effect of the Janus for the ground state remains the same. Like, for example, manganese is a nil antiferromagnet, and we have the minimum energy for the nil. And in the case of the nickel, is a zigzag. This is not changing, but the magnetic anisotropy energy is changing drastically. It's very, you can see here that it's very enhanced. And also there's a change in the sign here. So from this to this. Now in this case, this means that this nickel is in plane, and in the case of the Janus nickel PS3 with selenium is out of plane. So this is a drastic enhancement of magnetic anisotropy, and also this possibility of changing from in plane to out of plane. Then we go to the Wannier Hamiltonian. In this case, we need the orbitals of the metals and S and P orbitals of sulfur, phosphorus, and selenium. And we calculate the exchange interactions. And the most impressive thing here, but it comes from these broken symmetries, a drastic enhancement of the DMI. And this is reflected here. So these are the relation between the D and the J, so the isotropic exchange interactions. And this is reflected especially in the Magnon gap. This is the Magnon dispersion in the case of the manganese. And we can observe here that from the manganese PS3 to the Janus, there's a clearly effect of this anisotropy. This material has recently, I recommend to read this work by Libor Smejkal. It's now an archive that they are modeling and looking to the possibilities of making this material a possible alternative. Then more recently, we have been investigated also the properties of iron, gallium, tellurium. This is a very interesting material now because the Curie temperature is above room temperature. And as the material is isostructural with iron, germanium, tellurium, we want also to compare the properties and investigate why in this case is much higher. So what is the origin of the above room temperature? It has been, we have been working on that, and in this very recent published paper in Nano Letters. And is the idea of studying these two, gallium and germanium, to understand these effects. So here is the bulk unit cell. In this case, the iron, gallium, tellurium has a Curie temperature of about 380 Kelvin. The case of germanium is 230. And these are we have here labeled the magnetic atoms, the iron 1, iron 2, and iron 3. So we are computing this, for example, J12 is the interaction between iron 1 with iron 2, out of plane interaction. This is 1,3 from this to this. And then we have also this in plane, from iron 1 to iron 1, and from iron 3 to the next neighbor in the next unit cell, iron 3. So here is the main effect. Like when we take the J12 and J13, we don't have that much difference. The interactions are very similar. And in these cases, we are taking more neighbors. So this is like J1 to J2, but then to the next J2, to the next until 16 angstroms. We can observe that more or less are the same. But when we go to the in plane interactions that are in the same plane, so iron 1 with iron 1 or iron 3 with iron 3, we have a drastic difference between the iron gallium that is ferromagnetic and the iron germanium that is antiferromagnetic. We also explore the possibility of having a monolayer of iron gallium tellurium, and we calculate the phonon dispersion, and the system is stable, so it's possible to exfoliate it down to the monolayer limit. And we could observe the same behavior. So these properties are 2D properties and are clearly here that this behavior is the same as in the previous slide with the bulk. Then we can go also to the mechanisms to see exactly which are the orbitals that are responsible for that. And in the case of the iron gallium tellurium, we have this ferromagnetic, this is yellow here, these ferromagnetic interactions that go from the DYZ orbital to the DXZ. These are the main interactions that are favoring this J that is now ferromagnetic. And it doesn't appear in the case of germanium. Germanium is not mediating this effect. And it has these antiferromagnetic interactions here that are more strong. And in the case of the J33, we have the same. In this case, this is a little antiferromagnetic here, is affecting a little bit between this iron 3, but here is much more drastic, the effect of an antiferromagnetic interaction along the Z square to Z square in the case of iron 3. So this is making this exchange interaction smaller in the case of germanium, and explains why this has a higher TC. So some take-home messages from this talk. I was showing that 2D magnetic materials are a fascinating playground. They have many possibilities to explore and control the magnetic properties. We can play a lot with them. Ab initio calculations combined with tie-binding models provide fundamental understanding and also guidelines for the rational design and optimization of new materials before going to the lab. And also the versatility of chemistry can provide new ways to tune the magnetic properties and design new fields with tailored properties. For example, in the field of magnonics, it could be a new research direction, combine chemistry with solid state physics. So here is the most important slide, the group, the people that are working very, very hard in all these projects. We have also funding from the European Union with the ERC grant to the Smarties and the Valencian government. This is the project 2D Swims. Here are the main collaborators that have been involved in the experimental testing of our calculations in some of the projects I show today, but also we are establishing and we are developing collaboration with all these groups. And finally, I thank you all for your kind attention and opening for questions and discussion. Thank you.
Okay, thank you. Don't know if Igor, let me see, Igor, where's Igor? I don't know if he, okay, maybe Igor, can you unmute yourself and ask the question? So
no,
Igor,
that was the question was to the first part of the talk. I was just wondering why, how come that you have such strong contribution from EG super exchange if both EGs are unoccupied?
Yes, in this case, well, this is interesting because we have the occupation of the EG comes from a covalent bond with the iron, with the ion, no, with the ligand. In this case, for example, we have the sulfur and the bromide, and there's a chemical bond where there's electron density that is not perfectly ionic. We don't have exactly a chromium 3+ that is the
I'm sorry for interrupting, but ionicity has nothing to do with that. You are talking about distorting the octahedral environment, so the separation into T2G and EG manifolds is not exact. Is that what you mean?
Yeah, that's the point, no? That when we take the crystal field, we have like assumption of this is a perfect chromium 3+, and then okay, we can.
No, I'm sorry, but that's not correct. I mean, crystal field has nothing to do with ionicity. If your octahedra are perfect, that no matter how covalent your bonds are, you always have clean separation in T2G and EG. But I can see that in your case, the geometry of your octahedron is not perfect. So that might be that this is the case.
Yeah. But then, so in our calculation, we have these occupations that come, that this is sharing, no, with between
Right.
and then one thing is that when we are, for example, increasing the how are you, we increase the occupation. And this is something that we think it has to be severely taken into account, because how are you is the same for the T2G and the EG, and it shouldn't be the case because the population in the T2G orbitals is they are occupied and the EG are almost empty.
No, T2G, again, in the ideal system with full symmetry, both T2G and EG and G should be zero. Diagonal coupling should be zero, because you cannot hop without except across a crystal field gap. So it's only T2G. For instance, chromium triiodine, you don't really have anything but T2G. But in your case, you have both. And in fact, I now realize that T2G is even larger. That's interesting. That's very unusual.
Yeah, exactly. This distortion.
That's probably coming from this. Okay, all right, thank you.
Thank you.
Okay, so Alireza, go ahead and ask a question, please.
Yes, do you hear me?
Yeah.
Yes, thank you for your presentation. In one slide you showed about the gap in the chromium ionide at K point, and then you showed that by strain you can close the gap. I remember there were some discussion about amplitude of this gap, value of this gap, that DFT couldn't reproduce experimental gap. I'm wondering that, here, how large is this gap at K point that you found?
Yeah, it's very, very small. Like we have, I don't remember exactly the amount, but it's like 5 or 6 millieV, I think.
But is it in the same order of the experimental paper that people observed?
Yeah, of course this will be, because we are following this self-consistent field approach that it was implemented by Yuri Tinrov, and in this case the coincidence is, we think, is by chance, because we are very close, but this kind of calculation have more error in this case. But the important thing is that the difference between the iodine and the bromide and the chloride, and that we can reproduce with using a 0 parameter model. No, in this case we are introducing any parameter. It's fully.
And have you checked if there is Kita-F interaction in the chromium ionide as well as DMI?
In this case, we didn't test because we are applying the model directly in TB2J, but it will be interesting to check. Yes.
Yeah. Thank you.
Thank you.
My question that I would have is, do you have in the strain itself, how do you control the type of strains in the systems?
Sorry, can you repeat?
How would you control the type of strain that you would couple? There will be, is it just from the substrate only, or do you have other means to control the degree of shear to tensile strain?
Yeah, well, in this case, we don't have a substrate, so it's we are applying a strain to the lattice parameter, and we are allowing the coordinates to adapt for each step. So we are simulating like a perfect
a relaxed system, yeah.
Exactly. And for example, in this case, we are doing uniaxial strain along the A and the B axis. And for this case, for the chromium 3 halide is biaxial. Interesting will be to also to test, for example, if with a substrate we can get this kind of effects, like how is, because the material naturally is happening, like when people are measuring the bulk, we have expansion of one axis, a compression on the other axis, but then when we are going with a few layers limit, how is going to be this effect, no, in the lattice parameters. But this is what I think external strain.
Okay, very interesting. Do you have, I mean, because I think particularly shear strain, I think would be a very interesting thing to have in the electromagnetic system, to see if there's any means to produce it by clamping or something like that. I'm not so sure. I mean, theoretically, of course, you can always put it in,
Yeah.
but has to be connected to how the two would actually come into.
Yeah, we're very interested also in, for example, taking a multiferroic material and see how with an electric field we can play with the coordinates, or distort the coordinates and see the effects, no? Like connecting also with using different kind of manipulating the atomic coordinates with external stimuli, for example, with an electric field will be also, or like a kind of heterostructure, no, with a ferroelectric, for example.
Okay. All right. Perfect. Any further questions from the audience? I don't see any. You can stop sharing if you like. I think, by the way, you're
Frozen, no?
You're frozen. I think if you turn on and off your your video, maybe this freeze. Okay. No, it's still frozen for some reason. I don't know why.
Yeah, I don't know, because
That's all right. It's okay. It's coming on. This doesn't matter.
the
presentation was fine. The presentation was perfect. That was actually, except, I mean, the mistake was me coming late with all this. The problem is that I'm in USA, and then somehow they didn't like that I was in a different country until I log in. So it took a long time. I apologize for the delay today. Hopefully it won't happen again. Because of that, we've recorded the thing on the line, on the cloud, and it will take a few minutes, an hour or so, to actually upload it, as usually it's like immediately on the YouTube channel. But unfortunately, that's going to be delayed a little bit today. Oh, yeah, I think you're back on. Okay, you're back on. So today will be a little delayed on when it shows up in the YouTube channel. Usually comes immediately after, because it's a stream line, but in this case we didn't stream it for the few people, but we're a full 70 people today, so I thank everybody to have waited a few minutes that it was delayed. I apologize for that to Jose as well. But very interesting talk. Also, by the way, you may want to contact Igor. He mentioned that he wanted to talk to you afterwards. I'm going to stop the recording now. Stop the recording.